In this video, we'll talk about how we can also use integrals to find total masses of objects given their density, which could be varying over the length of the object. So the idea here is the same as pretty much what we had before, where we went from an area, integrated that over the length to get the volume. In this case, we want to take a density, integrate that over a length to get total mass. So the basics of it is the same, where we're going to chop things up into little pieces and then use that to give us the answer. So if I have an object, like a rod like this, I want to find the total mass of it. And say the density varies as you go along. A way this could work is if you have like an alloyed material where at one end it's entirely one metal, the other end it's a different metal, and it sort of smoothly transitions between the two, that would give you a varying density throughout the length of the rod. So our idea here is to, again, break this up into little pieces and then approximate the mass in each little piece and then add those up to get the total mass of the object. So I can chop this into pieces. If I look at one of these guys, I want to find the mass of this little piece here. Now, if the density of the actual rod is varying across the length, the density of this piece is also not going to be constant. However, because it's a small piece, we can approximate it by assuming that it is constant. And so in that case, the mass should be the density of the piece times the length delta x. Right, and this is assuming that our density rho here is density in terms of mass per unit length. It's also called linear density. So if we have that, then the total mass of this object should be the sum of the approximate mass of each piece. We're going to assume it's constant on each piece by picking the value somewhere inside, and then add those up over the entire object. So the total mass should be a sum over however many pieces we have, the approximate density of the kth piece times this delta x, and we're in the exact same picture we were before, where it's in the limit that should turn into an integral to give us the mass of the object. Where now here we represented our density rho as now a function of x, which is generally the way it'll be given in a problem like this, as opposed to the sort of approximated on each slice. This is the exact same idea that we had before, going from areas to volumes in the previous videos here. I can approximate each little piece by a cylinder, which has constant area, which gave me area times delta H gave me my volume. I add those up. In the limit, I get an integral. In this case, I can approximate each chunk by a chunk of constant density, and then add those up to give me my approximate mass, and if I take the integral, then I get the actual mass of this object. So now let's see an example of what this might look like. So assume that a 2-meter long metal rod has density given by 5x minus 1 squared plus 2, where x is the distance in meters from one end of the rod. What is the total mass here? So if we draw out a picture again, we have our 2-meter long rod, and the density is given by this function. Just sort of plot out some values. At the midpoint here, the density is 2. Over here it's 7. Over here it's 7. Basically, this is sort of a rod that is less dense in the middle than it is on the edges. And that can happen when you're trying to stretch out a metal. You get some sort of alloy type thing that does that. This is entirely possible to have happen. So how do we find the mass of this rod? Well, I just want to integrate this density function over the domain. So I just want to integrate from 0 to 2 because x is distance in meters from one end of the rod. So I can set 0 over here. X equals 2 is the right end, and I can do the integral. 5x minus 1 squared plus 2 dx. We can simplify this out, and then we can just find the antiderivative and solve from there, which comes out to 22 over 3, that mass. And since this problem didn't have units on it, we don't have units on our answer, but if this density be given in sort of kilograms per meter or grams per meter, you would then have that as your answer as well. So that's the idea of finding massive objects using integrals. It's the same as the other stuff we talked about before, basically figuring out how is this mass of the object some sort of totaling procedure, and then what do I have to integrate in that to add up to give me the total mass of the object.